Hi, I'm Nikki Lacey and I'm the founder and director of Nicola Wilkin Limited, and I've been creating teaching resources for a number of years, but before that I was a head of department at a boys' school where we taught computing and programming, and before I became a teacher many years ago I actually used to be a programmer as well. So that's just to give you a bit of background information on me. What I'm here to talk about today is the Jump 123 pedagogy, which is a really easy way to teach programming, and this is something I've developed over a number of years. So let's have a look at how we can teach programming to our students in a really effective way. So to start with, we have the theory of programming that we need to teach them, and also we have the practical skills for how to apply that theory as well in the programming, and they need to come together, and that can be quite tricky, is learning how to apply those skills to that theory that they've learned. And that's where I think Jump 123 is really useful. Now specifically, Jump 123 is split up into two sections. The Jump part is the pedagogy of how we can teach it really effectively and create and design great lessons, and the 123 part is about assessing pupils' programs in a consistent way. And I've done another video based on 123. This video is just interested in the jump part of the pedagogy, so we're going to drop the 123 for now and only talk about jump today. Now we have a student and they need to learn how to program, so we need to get that somehow into their brains, and we have something called the working memory. And the working memory is what they're currently thinking about and what they're currently working on, and that's got a very small capacity and it doesn't really get stored anywhere. It's a bit like RAM on a computer, so it's something that's only got a very small capacity and it's not something that's transferred into their long-term memory just yet. We need to find a way of transferring that knowledge that they're currently learning about into their long-term memory, so that later on in the subsequent lessons they can recall that information and apply it without having to relearn it again, or the frustrations as a teacher of having to go over old material that you thought they already knew. So the trick here is knowing how to transfer it from their working memory into their long-term memory. So when we're trying to teach a student about the basics, then we start off quite intensively really. So in that first lesson I often see, and I used to do this myself, I often see someone trying to cover input and print and strings, and then not forgetting variable. If we're inputting, we need to store it somewhere, so they need to talk about creating variables, naming variables, assigning values to variables, and they also probably have a look at syntax errors as well, and that's a lot for them to take on board when they're first learning a program. So doing this all in one lesson, and it's something, as I say, I've done myself in the past, it just doesn't work quite so well. This leads to something called cognitive overload. Now cognitive overload is a term that came about from something called cognitive load theory, and that was developed by John Sweller in 1988. And he states that our working memory is only able to contain a small amount of information at any one time, and as teachers we really need to avoid overloading it, because that actually stops them being able to transfer it into their long-term memory. So in order to maximize learning, we need to reduce the cognitive overload that students often suffer from, and we don't realize that they're suffering from. Now there's several types of cognitive load that a student might be experiencing. You've got the intrinsic cognitive load, and that's how complex the subject is to learn. So text-based programming can be quite technical, and so there is an intrinsic cognitive load there which is difficult to maintain, and students will quickly overload on if we're not careful. You've also got the extraneous cognitive load, which is external factors that can complicate the learning process. That can be things that are outside your classroom, but also it might be things that you're doing as a teacher, which is adding to this extraneous cognitive load. And then finally we have the germane cognitive load, which is the effort it takes to process new information, and students' levels there vary greatly. So how they can integrate it with existing knowledge, so what memories have they got what experience have they got that they can actually relate it to. And so that really is personalised for every student. So everyone's cognitive load is different. They'll have different experiences they're coming from, they've got different stresses going on in their lives, and so their capacity can vary quite a lot. And as a teacher, we need to be very aware of this, so we're not adding to it if we're expecting them to be able to transfer things into that long-term memory. So if we go back to the cognitive load theory, the overload actually prevents us from transferring new knowledge and skills from the working memory into the long-term memory. So we do actually need to take this on board. It is a really important theory about why some students might be struggling to learn things. So when we are presenting them with the theory of programming and the practical skills, that's an awful lot to be taken in, and quite often where these mesh together can be where cognitive overload can easily occur. Another theory I want to talk to you briefly about is the legitimation code theory, and this was by Carl Mayton in 2013. Now, part of this you might be already familiar with. It's quite popular in education circles these days. It's called the semantic wave. If you've not heard of it, don't worry about it. I'm going to explain what it is now. So when we look at the semantic wave, it's really a graph of how we learn technical subjects. So really it is to do with technical subjects, of which programming happens to be one. So we have time passing at the bottom there. At the top we have the level which shows something is hard to understand, and at the bottom something's easy to understand. And when we're learning, we have this semantic wave, and this is shown by the green line here. So in programming, let's have a look at how that actually works. So we need to introduce the abstract concept. So for instance, for loops. That's quite an abstract concept for students. So you need to introduce that and the technical terminology so they know that's what they're learning about. But then we need to break it down, explain it in terms that they understand. So use examples and metaphors and diagrams until eventually the student is able to relate it to things that they already understand and they've got some sort of focus point on. So it's much easier to understand. And then we need to start building it back up, so we repackage it and link it back to those abstract terms. So once they understand what a for loop is, then we have a look at how that's done in programming, and so they actually understand that abstract concept or the technical term a lot easier. So that's what is known as the semantic wave. So let's just have a look at a student. Here they're going to be learning about an if statement. So not only do they need to learn about the technical terminology of using if, answer equals, speech marks yes, speech marks colon. There's a lot of technical things in there that they need to remember. They also need to understand the abstract concept of how an if statement is constructed, so you might be showing that in a flowchart. But they also are learning at the same time about problem solving, creative thinking and resilience. There's an awful lot that they are trying to take on board all at once, and that's where we can get this cognitive overload from. So as a teacher, as we're talking to students, we often don't really see things from their point of view. They're looking at it from a young person's point of view, whereas we're looking at it from an adult's point of view with our own experiences. And so quite often when we're trying to teach something, we're actually reflecting back ourselves about how we would like to learn it. And that's not necessarily great for the students. We kind of almost ignore the students' requirements and we're just looking at how we would learn it best. And we've also got rose-tinted glasses about how we learnt it, and we forget about the struggle of understanding what a string is, for instance, or a variable, or what we mean by assigning a variable, why we have a single equal symbol and other times there's two equal symbols. All of those are things that after a while, if you are a more confident programmer, you take for granted, and you do need to explain that to students, what the difference between a single speech mark and a double speech mark is, for instance. So if we go back to the semantic wave, we do need to have a look at that abstract term, break it down into terms that they will understand and that is relevant to them before we build it back up into the technical terms again. And that's where I think JUMP is really useful at helping us plan really effective lessons that are going to be useful for students. Now we've got more of an idea of where they're coming from, we can use JUMP to help us do that. So let's just have a look at an example of something that I've seen far too often in people's lessons. It isn't necessarily the first programme that students would have seen, hopefully not, but it's something that they might see a few lessons in. And really what we want to focus on in this lesson, for example, would be using div and mod, so whole number division and finding the remainder. So really it's that little bit of the programme that we're focusing on. And in order to do that bit of the programme, then we do need to assume that they already know about input and print. So there are things that they would also require for the programme, but hopefully that they would have some understanding of before this. So when I teach my lessons, I would have hopefully covered print and input and int before they get to the stage where they're doing div and mod. But that's really the only part of this programme that's important to the student when they're learning this new skill of div and mod. However, I see far too often that people are including all the other things. They're including subroutines, they're including comments, they're including returning values, calling functions, and it all gets very messy. And this is adding to the cognitive load of students. We need to really think about what is it that we want to focus on, what is it that they need to be learning at this time. And okay, it might be nice and it might be good practice to use subroutines, particularly when you get to more complex programs. And as a programmer, I know the value of using subroutines. However, when a student is still learning how to do these sorts of calculations, they don't need to know about subroutines just yet. That can be something that's introduced much later on. And as a programmer, I found that most programmers, we are inherently lazy people, and therefore we're always trying to find the most efficient, the most simplest way of solving a problem. We want to solve a problem in the least number of lines of code as possible, and that's one of the joys of programming for me, is trying to find the simplest solution. And this solution that's on the board here is not the simplest solution. It is overcomplicating it. The simplest solution would be this program here, where you're just getting the crux of what you need. And that's the way we need to think about it when we're teaching our students. Yes, it might be a good idea to define subroutines, but that's something that they don't need just yet. They can learn that later on when they need it. Doing it for the sake of it, because it's good programming practice, because you just do it that way, isn't necessarily the right way to think about it. So sometimes we need to focus on what we want to do. So let's have a look at this student. They are in their first lesson of Python, learning what Python is, and they are being presented with print, strings, input, creating variables, naming variables, assigning variables and syntax errors all in one go, and that is cognitive overload, as we know. That is too much for them to learn properly and be able to transfer it into the long-term memory. I've taught lessons like this and you think that worked well and they've understood it. However, 2 weeks later I come back and they are not too clear on what an input statement is or a print, or why some things have speech marks around it and some things don't. It's because they've not transferred that information into their long-term memory. They only had it in their working memory so they could do the activity in that lesson. However, we come back to it after half term, they have no recollection of it whatsoever. It's not in their long-term memory. And then I have the frustration of having to reteach it, because some people have got a vague idea, some people don't understand it. It's much better to make sure it's taught properly in the first place and that students really understand it. So instead of covering all of this in one lesson, now what I do is I simplify it. We only look at print, strings and syntax errors in those first lessons. We don't worry about input, we don't worry about variables. Print, strings and syntax errors, make sure that they understand that and they know the nuances of it as well. One of the things we need to think about with teaching programming is vastly reducing the amount that they are trying to learn in one go. It's not about how much we can teach them in the shortest time possible, it's really about helping students become the best programmers possible, and that means they need a really secure knowledge of these basics before we move on to other things. So it's not about how much you can cover in a short time, it's really about doing it properly and learning it properly in the first place. Now, one way that I do that with JUMP is to split information into chapters. So I split a lesson into chapters, much like reading a book in those heady days of when we had proper paperback books, which I still do like to read a proper paperback book. then I would always, if I was reading on a beach or in bed, I always think I'll just finish that chapter, I'll just get to the end of that chapter before I put my bookmark in, or God forbid, fold down the corner of the page. But it's a nice ending. We understand chapters, give us that complete bit before we go on to the next thing. And that's how we should think of chapters in our lesson planning. So this is taken from a slide in my actual first lesson where I display the chapters to the students. Now I call it Steps to Success. And so they would be looking at text-based programming, strings, errors in the code, and creating a string. So we split it up into separate chapters, and each chapter really leads on to the next one there. So when we're looking at strings, they actually would be introduced to a print statement as well, but when they come to then looking into more detail, then we'll start thinking about why we might have speech marks in there, and that leads us on to errors in our code, which then leads us on to when they create their own strings with print statements, they can recognise that why it's not working is because they missed off the speech mark or whatever it happens to be. So there is a nice flow between them there. So if you have a look at how chapters might help in a lesson, so we've got our lesson, we've got our semantic wave barriers there, and I've actually split it up into the different chapters. And for each chapter we have our own semantic wave. Now these are much lower because it's much easier what they're learning. It's a shallower wave. There's not so much that we're introducing right at the beginning of the lesson. So to start with, they would have a text-based versus Scratch lesson. So then we'll have a look at how they would be comparing the two. Then we would go on to strings and looking at the nuances of strings, errors in their code, and then finally they'll be able to create it. So each of those have their own semantic wave. So there's several semantic waves throughout that whole lesson. So let's have a look at JUMP specifically. And what does JUMP stand for? JUMP stands for judge, unpack, modify, and finally program. So it's a nice mnemonic to remember, and this is the types of activities that you can use to help you achieve that semantic wave. So judge and unpack really are dealing with the theory of the programmings. That's where you're covering the abstract concepts, and modify and program at the practical side of programming. So let's have a look at them in more detail. So judge. This is where we're looking at the big picture view, and students can give opinions. So we're looking at a program or a piece of code as a whole rather than looking at the detail of it. So the questions you might ask could be, what do you think this program will do, or what will the output be? How could this program be improved? Why do you think this program was created like this? Why do you think the program will not work, or what type of error will we get? So all of those are taking the program as a whole. So judge is looking at the big picture view. Unpack is when we start getting a more detailed view, and we're drilling down into the mechanics of the program. So here we're looking more at the syntax or the specifics here. So can you identify the variable, input, selection, whatever it is that we want to focus on? What would happen if we altered this? What would happen, what would be a suitable input to generate this output? So then you're looking at maybe the condition and if statement, so you're specifically looking at that. So how would you get too high? What would you need to input to get too high? Whatever the condition happens to be. How could you alter in this part of the program to do whatever it is you want? So you're then looking at specific syntax or specific lines of code, particularly if it's a larger program. Then we have modify, and that's where students can experiment and alter parts of an existing program. So that might be your previous program, so change your previous program so that whatever, it could be the program that's been given to them. So what happens when you alter your program so that it does this, add to the program so it does that, leave it quite open, improve your program, or find and correct the errors in a program. So it could be either given to them or altering or modifying their existing program. And then the final one is program, and this is where they're creating a new program using different prompts. So it could be create a new program that will, and you're giving them some written instructions and a written algorithm, or create a program from this flowchart, Or it could be that they do a bit of planning first of all, so draw a flow chart and then create the program that will, whatever it happens to be. So that's where they're creating a new program. So judge and unpack are the theory, so judge is the big picture and unpack is the detail. And for the practical side, you've got modifying existing programs or creating new programs. So that's the 4 different parts of JUMP, and by bearing those in mind, you can create more interesting lessons where you're looking at the theory and the practical. So let's see how we might apply this in a lesson. So we've got our 4 elements here: judge, unpack, modify and program. And in our graph we've also got our 4 chapters going on there. So for chapter 1, which was in this example comparing a text-based program with a block-based program, so they're looking at Scratch and Python, then there might be a couple of judging there, like what do you think this program will do, and then they're unpacking it where they're looking at the differences and the similarities between them. And then for chapter 2, where they're starting to look at strings, they might be presented with a print statement with a string in it. Then they're asked to judge what they think it would do. That might be a paired discussion. And then they're unpacking the individual details of that string or print statement. And then they might have a go at modifying it to see what happens when they remove a bracket or change print to have a capital P or whatever. Which leads us nicely then onto looking at the errors in a program. So again, you can unpack it and specifically ask them to change those bits or to what they think will happen when those pieces change, and then correct a program which has got a load of different errors in it. And then finally, they're going to have a go at creating their own print statements in chapter 4. So I might have a load of unpacking questions just to make sure that they are secure in that knowledge. And then finally they have a go at programming their own new program. And so for each of these we would have the semantic wave. Now those activities are not evenly spaced along there, as it showed on that previous slide. They are going to be used specifically to help that semantic wave. So in chapter 1 we'll have some judging first of all about what they think this text would do, and the differences between the same program which is displayed in Scratch and displayed in Python, and then the specifics of looking at the different code that's used there. So then they start repacking it up again. Then for chapter 2, which is about strings, then they can do a judge and unpack right at the beginning, and then the modify might be used for repacking it at the end of that semantic wave. For chapter 3, which they are then looking at error messages, then again you can use questions throughout that semantic wave, and then a modify to really repack it at the end. And then finally for chapter 4, where they're creating it, then you could just use lots of questions to really make sure they're secure in it, and then the final repacking with the program. So that's one way a program might have achieved those semantic waves using the JUMP activities. Here's another lesson where they might be packaged in a slightly different way. So you can see we've got some JUMP, we've got some unpack, we've got some modify, and we've got some programming tasks. And you don't need to have all of them in one go, and you don't need to have them in order either. You can jump around with JUMP, pun totally intended. So instead of going through thinking I've got to have a judge, then an unpack, then a modify, then a program, that's not the way it works. You would use them whichever way you want to help that particular part of the lesson, and you don't need to include all of them in every lesson. Some lessons it might not be suitable to have a modify, maybe you want to spend longer on programming it. As long as you're spending a bit of time looking at the theory and looking at the practice, then students will be able to get those skills. So it's whichever you need to use to help you, but bearing in mind that semantic wave needs to be completed for each chapter, and we're breaking it right down each time. The final thing for JUMP really is giving them time to practice. Students really need this time to practice. They can't just retain it without having a chance to have a go. So they need time to transfer it into from their working memory into their long-term memory and be able to retrieve it later on, so they need that time. So every few lessons I generally have a lesson where I'm not teaching them quite so much, maybe one or two very minor things, but really the plan is to just give them practice time to consolidate everything they've learnt at that point, which is useful because obviously some students will miss the odd lesson, they've got a school trip or they're just ill one day. So it's quite useful to be able to have that time where you can catch up with everyone, but also those faster students would love the challenge of just programming one after another, and the students who are struggling with it, you can spend the time with them and have a look at their misunderstandings and sit down with them and give them that one-on-one time that they require. So this is taken from one of my lessons, so they would have learned at this point how to input, how to print, how to use addition, subtraction, multiplication, division, div, mod, integers, float and string. So they would have known all of that sort of basic thing. And so then in this consolidation lesson, then they would be given 3 different programs to do in quite quick succession, but they wouldn't need to do all of them. So here's the first one: input 3 numbers, display the average of those numbers. The next one is convert a temperature from Celsius to Fahrenheit, and I give them the maths. If it's a streamed class and they're quite high level set in maths, I might not give them the mathematic formula there and expect them to know it, but otherwise I would give it to them. Another one is to ask the user for a number of minutes and then work out how many hours and minutes it is. So they're all variations on a theme. They're all using those focus skills that I want them to look at. But if it doesn't matter if they just do 1 or if they do just 2 or if they do all 3, they're still getting that information from their working memory more into their long-term memory. And as I say, faster students who can whiz through these, then they will be kept occupied for longer by having 3 displayed, whereas others, they know it's okay to just make sure they're getting 1 working correctly. So you need to give them time for practice, and then later on in the same lesson, once I've introduced F strings, which is just a little extra thing that I would do just to feel that they're learning something new, then I would give them some more activities. So really this is about consolidating what they already know. F strings is a nice extra that they appreciate. But they would then work out the circumference of a circle when the user inputs a radius, and again, we're giving them the maths is optional. They can then expand that, so they work out the area of the circle, and then they would work out the volume of a cylinder. So you could have it so they're 3 separate examples that we did in the first lot, or they could be expanding the same program. But again, it's just giving them reinforcement and altering the code slightly so they're looking at the nuances of the code, and that is really useful. So when it comes to creating effective programming lessons, then I use JUMP as a checklist to make sure that they are the best lessons from that student's perspective. So we focus on the essential skills and knowledge and reduce that cognitive load. We don't try and cover so much. We use chapter-based lessons with the semantic wave to introduce and reinforce new concepts. And I apply JUMP elements to plan varied lessons that have effective activities which give them that broad range of skills that they need. And finally, we ensure students have so much time to practice and transfer those skills into their long-term memory. So that would create really effective lessons, and that will help them become better programmers and reduce the frustrations of having to go back and reteach things because they've forgotten it. So hopefully that's given you an insight into what JUMP is all about. If you would like some more information about JUMP 123, then please go to my website jump123.co.uk. Thank you very much.